The next talk is by Professor Diwakar Venkatesan from JNCSR, Bangalore. And he's going to talk about interfacial instabilities in microgravity conditions.
Yeah, good afternoon, everyone. My name is Diwakar. I'm from Jawaharlal Nehru Center for Advanced Scientific Research, not far away from here, in further north of Bangalore. So what I'm going to talk about, you would have had many talks about biology, but slightly detour towards physical systems, and we are going to talk about fluid systems in space, try to understand some interesting features. That's what we are going to do. And in fact, we have a payload that's going in the Gaganyaan mission, and essentially the scientific team involves myself, Professor Farzam Shiosthia from University of Lille, and Professor Ranganarayan from University of Florida. And we have, a couple of problems that we are interested in looking at in this payload. And the first problem that we are interested is what is called as the classical Faraday instability. So it's a very simple problem where if I have, a fluid and I do a perpendicular vibration, that means I give an oscillation that is perpendicular to the interface that I have. So you see these sort of, interfacial waves that come. And essentially, they are resonant problem. There is a resonance there. You have a resonant phenomena. There is a natural frequency to the system. You excite, and what you see is a manifestation of the resonance that happens. So you can do both type of, you can think of this happening in a immiscible combination, miscible combination. Many things you can envisage. So the question is, why do we care about such a problem? Essentially from many practical applications. One is, droplet generation for drug delivery. You can do microassembly for liquid-based templates. You can do bubble breakup under vertical vibrations. And also, these problems give you fantastic, play field to understand quantum analogs. So you can do quantum tunnel. You can sort of, mimic the effects of, particle diffraction, quantum tunneling, so many other things that one can do. Okay, but then the question is, why do we care about this in a space scenario? Okay, the essential culprit here is what we call as G jitters. So let's say you have a space system, a spacecraft, and there is motor running somewhere. So okay, normal, there could be motor running somewhere here or something, some machine running, and I won't feel the vibration because there is already a gravity that is sort of keeping me sustained. But when I go to a microgravity scenario where there are fluctuations, if there is any fluctuation that is created by some system which is running, so it's going to have a fluctuation in the 0G. And that is a problematic thing, because that's going to trigger this sort of instability, this sort of vibrations on the surface. And the problem is, let's say you're going to store liquid, and we don't know whether these vibrations are going to make them undergo transition where they start mixing in a critical way, and then they lead to, again, instabilities, catastrophic scenarios. So we want to understand why this behavior happens and how to prevent this. And also the other important application, people talk about is bubble removal. So let's say you have a circuit and there's a small bubble inside the circuit. In normal conditions, it's like, buoyancy would take it away. You don't have buoyancy, so it's going to be a serious problem. So this is what is the issue. And the question is, what do we know about this instability? See, normally, what do I think? I would think, okay, now suddenly if somebody, put me in a centrifuge, I would think that if the gravity is increased, it would be difficult for me to provoke this instability. That means my normal intuition would tell me if the gravity level is increased, the stratification should become more predominant, and it's going to be difficult for me to create this undulation. But what we were able to show is that it's not the case. It's a frequency-dependent phenomena. That means when you have a low frequency, okay, when you excite the system at a very low frequency, it is actually the terrestrial system which is more stable. Okay. Whereas when you go higher and higher frequency, it is the zero gravity system which is very stable, which is very counterintuitive. And this is what we wanted to understand, why this transition happens and why this sort of a behavior, comes in the system. So the question is, there are many scientific questions. I'm not going into the details of it. I would like to, show what we, go to the physics of it to understand many things. And so the question is, we want to, if you look at the surface tension, the natural frequency here, it depends on few parameters. Primary of them is, of course, the fluid density, density difference between the fluids, and the interfacial tension. But the problem is, under normal Earth conditions, you can never understand what will be the influence of interfacial tension. So essentially, everywhere you do experiment, the gravity is going to be the culprit, which will never allow you to understand the effect of interfacial tension. But then when you go to space, there is no gravity. Everything will be driven by interfacial tension. And so this becomes a problem. And so what we did, we have developed, this is the work that we have done already, with using a binary fluid combination. We have developed a setup where we did parabolic flight experiments. And so this is where we have a binary fluid combination. What we do is we heat the fluid, actually it becomes miscible. And when you cool it, it becomes immiscible. So there is a consolid transition happening at around 42.5 degrees centigrade. So which, it's what we do is we just fill the cell, you change the temperature, you can actually understand the effect of this Faraday instability both in the immiscible limit and the miscible limit. So when you do these experiments in ground, this is the behavior you get. That means, for different frequencies, if I try to see at what amplitude, there is an onset of undulations. Okay, so what we see that there is a banded behavior. That means for certain ranges of frequency, you see certain modes, and you see when you increase the temperature, you see that the modes are actually shifting leftwards. Okay, and this is essentially because in this system you will see that the natural frequency is actually dependent on ρ1 minus ρ2 into g into kappa. Okay, on Earth this part is sort of negligible. So essentially, when we in this binary fluid system, when we heat it, actually the density difference comes down. So when this comes down, essentially the kappa has to increase. Okay, so if my natural frequency is kept constant, in case if I'm for a given value of wavelength, okay, the wave number, essentially if I reduce this, the natural frequency must reduce. So that's what we see, that the shift in the mode. And we also see an interesting behavior here, that when you assume the asymptotic behavior, you think that when you approach this constellar behavior, the interfacial tension value is vanishing. So you would normally think, okay, it should be easy for me to create instability. But what we see is an interesting thing is that actually it becomes difficult to create instability. And that behavior, again, comes back from this expression, where my density difference comes down. If my natural frequency is kept constant, this must increase. That means now the waves become more choppy. There is more viscous dissipation, and I need more amplitude for provoking the instability here. And so what we have done, we wanted to understand this behavior in microgravity scenarios. So we have done quite a few parabolic flight campaigns in France, so as a part of the French Space Agency and the European Space Agency campaign. So what we do is, it's a normal passenger aircraft, but modified for special purposes, where you take the aircraft, you put it at 45-degree inclination. After some point, you just cut off the engine. So it goes like a projectile, where the centrifugal force would balance your gravitational force. And you get 15 to 20 seconds of 0G. And then you will again have hypergravity. And then you will continue with the flight. So I've done 341 parabolas myself. So I do have a Yuri badge where it says that I've spent more time than Yuri Gagarin in weightlessness. Okay, so these are the different setups that we had built, and this is how a simple, you can see here, it's going up, okay? So it's at 30-degree inclination, 40. So this is the start of 0G phase, where you can see my colleague expressing, experiencing weightlessness. And this is the interfacial waves that you see here. And you can see with the horizon, the aircraft is going down. And it's as if that, you can see from the cockpit, it's going to hit the ocean. And again, you come back. Yeah. So again, we were able to understand what is happening in microgravity, where you are changing the frequency and the amplitude and the temperature as well. And we could clearly again go back to this expression and understand what is happening. Again, here the G is not present. Again, the competition is between the interfacial tension and the wavelength cube. Okay, and that leads to this sort of choppy behavior, and we were able to show the preliminary results where we see this sort of a crossover behavior. That means that beyond certain frequency, actually it is the microgravity effect. At microgravity, things become much more stable. And the explanation is pretty simple. You can think of a simple pendulum experiment where you have a pivoted pendulum and you are vibrating the pendulum. A pendulum is oscillating, and suddenly, let's say you are changing the gravity. Okay, the only way the system can respond is to sort of undergo, if the natural frequency is kept constant. So the only way it can do is to change the wavelength, and that's what we see. So when you reduce the gravity, there should be a corresponding reduction in the wavelength, and when the wavelength reduces, there is more dissipation, and that leads to more stability that comes from the microgravity conditions. How many minutes? 3 minutes. Okay, good. So this is what we want to do, but unfortunately, these parabolic flights, they come with 15 seconds time. It's impossible for you to do more detailed analysis when you're going closer to the critical point. I mean, when you want to look at the critical transition, you need to wait for long duration to even observe anything significant. And when you want to do miscible experiments, that means you want to sort of increase the temperature in this binary fluid. You want to see how the transition happens in that scenario. You need a longer time, and it's impossible for us to do in this parabolic flights, and that's why we go with Gaganyaan, where we are developing this payload, where we are doing this Faraday setup is being put, where we will do these oscillations with temperature control and with high-speed imaging. We try to understand the behavior here. So along with this, we also have one more setup that goes to understand the Bernard-Benangani experiment. I mean, where you have two fluid layers, you are going to heat it from the bottom, and you will see this sort of external patterns coming. So this, we have done some analysis in multiple layers to understand what the behaviors are, how the transition is going to happen, what type of oscillator transition is going to happen. Okay, the interest comes from two important problems. One is to understand earth mantle convection, because the mantle convection theory talks about multiple layers of mantle and the thermoconvective instabilities occurring there. And the other problem is what we call as a liquid encapsulated crystal growth. That means you want to grow crystals in space. Normally what you do, you sandwich one layer between two fluid layers, and then you slowly remove heat. But you don't want that to provoke convection, because once you have convection, there is a chance of getting bad quality crystals. You want to avoid that. So this essentially helps you understand this, and this is one of the objectives that you want to see and go into the depth of understanding this multi-layer Bernard convection in system in microgravity. So this, we do some preliminary experiments in the lab, and this is the payload design where we have two bottom block that will be doing heating and top block might do the cooling. You could do the other way also, shouldn't be a problem. And we have the fluid layer that will be sandwiched, and you can heat or cool whichever you want, and then we'll put some aluminum flakes to understand the pattern of convection. So the other important problem that anyone would face is, okay, in normal conditions, if I sort of mix two fluids, if I just keep it here, it's going to settle down. It's very easy. The phase separation is done by gravity for you. But then when you do it in space, it's impossible for you to separate these fluids. Okay, when you demix them, they are going to form emulsions. Then the question is, how do you segregate them? So this is one, in this Gaganyaan payload, what we do is we do centrifugate. Okay, but then in future missions, we want to see whether this acoustics could be used as a means for phase separation. So this is one problem we are interested. And apart from that, the other problem that we want to look at is doing 3D printing in space. Okay, so primarily doing optics, because when you have an optical component, you want to do some in situ repair in space. So this is one technology that's available on ground, where they do develop lenses and other optical components by means of liquid droplet printing. And what we want to do is to emulate such a scenario for microgravity conditions, because here it's basically the fall and everything is aided by gravity. So we wanted to see how that can be done in space. So this part I skip. So coming to the final thing, the next thing that we are interested is looking at how electrode deposition. See, because it's a very common thing that we do coating, we do electroplating, etc., for many practical applications that we know. But then the question is, how do these things change when you go to microgravity conditions? Because again, the convection pattern is affected, and this is one of the work that we are currently working on. So this is some experiments that we do on lab, and we would try to understand how the dendrites form, what is the structure of the dendrite, how its wavelength would change, etc. So here again, you can see the effect of gravity. When I keep the growth part, the test cell incline, you can see that along the direction of the gravity, you see the growth is quite predominant, whereas opposing the direction of gravity, you see that the growth is not that much. Okay, so this is something which we are trying to understand in detail. Thank you. Thank you so much for your time.
Okay, we have time for one very quick question, please.
Hello. Yeah, thank you for the talk. I was interested in knowing what's the effect of the viscosity stratification between the two fluids. Because since it's a binary mixture, there must be a difference in viscosities too, right?
Correct, correct. See, the
So
viscosity
what role would that play?
No, viscosity essentially tells you how what is the critical, see, if I go back to this expression by Landau and Lifshitz, you can see the viscosity is the one that tells you what is the amplitude that you get. Otherwise, if there is no viscosity, there is no amplitude. See, you see this expression. Okay, if I'm at the natural frequency, okay, it is only the viscosity. So this term is going to vanish. Yeah. So it is the viscosity that does play a role. So it is essentially the damping actually that leads to the critical amplitude that you get. The manifestation of that is because of viscosity.
Thank you.
Okay, maybe we can have more questions offline. So let's thank our speaker again.